All right, welcome to the first lesson of Unit 10. Unit 10 is on differential equations, and I want for a second to put some historical context on why we're learning this and why it's so important. Back when calculus was being discovered by Newton and Leibniz, scientists and mathematicians were really concerned with planetary motion and figuring out where planets and stars were going to be at certain times. And in order to do that, they needed to sort of track where they were going and the speed at which they were moving. And essentially what they were doing is writing equations that modeled the rate at which these planets were moving, which is a differential equation. And so by studying equations that model the speed at which things move, we can learn a lot from them. And so this is kind of the beginning of that. And the work that we have done with differentiation and anti-differentiation is sort of going to culminate here as we're going to be using both of those concepts in this unit. So with that being said, let's go ahead and start from the beginning. All right, so a quick little discovery problem here. Just go ahead and write down this equation, dy dx, and then answer questions A, B, and C. You don't need to write down those questions. So a function y that satisfies this equation for dy dx would be the function y equals x cubed. Because if I were to differentiate both sides, and this is really getting to part B here, with respect to x, what I would end up with is exactly the equation that I was given. Alright, so the derivative of y with respect to x is dy dx, and the derivative with respect to x of x cubed is 3x squared. So perhaps as you were differentiating, or maybe when you read question C, you realized that this is not the only function that satisfies this differential equation here. X cubed is not the only expression whose derivative will be 3x squared. Reason being is that any constant added on at the end will of course have a derivative of 0, right? Any constant function is a perfectly horizontal line, and the derivative at any point is going to be 0. And this means that there are infinitely many functions that would satisfy this equation, dy dx is equal to 3x squared. And so we can represent that by saying that the function y that satisfies this equation, dy dx equals 3x squared, is going to be y equals x cubed plus c, where c is any constant, right? Because no matter what, when I take the derivative now, I'm going to end up with 3x squared. And this is what's called a general solution to a differential equation. This, of course, being a differential equation. And you can guess why. I have a derivative, which is made up of two differentials, involved. So let's go ahead and define these clearly and then try out a couple of problems. And so here is that definition. An equation involving a derivative is called a differential equation. And you can think about for a second why that is. A derivative is made up of two differentials, right? dy over dx, the differential of y over the differential of x. Really what that is saying is an infinitesimally small change in y over an infinitesimally small change in x, which gives you that instantaneous rate of change. And so hence we have the term differential equation. And that's why in most situations when we represent the derivative in a differential equation, we'll use dy over dx. That doesn't mean that that's always the way we represent it, but usually it is. Now the order of a differential equation is the order of the highest derivative in the equation. So in the example we just saw, we had the first derivative, and so it's a first order differential equation. And we will see a couple of examples of some second order differential equations, and hopefully you stick with mathematics. You take a couple of differential equation courses in college and you will see many, many, many more examples. So let's take a look here. First example, the one that we just did, dy dx is equal to 2x. This is of course a first order differential equation. And I'm going to abbreviate diff EQ for differential equation to save myself a little bit of time here. All right, moving on down, here is another example. Here we have the second derivative of y with respect to x, which is equal to 7x plus 12, and that is a second order differential equation. So far, nothing too crazy here. Now here is another way of writing the derivative, as we've seen, we use this a lot. F prime of x is equal to sine of x. Here our differential equation involves the first derivative, so again, a first order differential equation. Moving on down, another way that we can represent the derivative is with prime notation, so this is y prime, which is equal to x plus y. Notice a couple of things here. The highest order is first, because I have my first derivative here. And also notice that this is not solved for x. And so we will see some situations where that arises. And we've dealt with implicit differentiation before, and so we should be used to dealing with situations like that, and it will not be too challenging, so don't worry. All right, now moving on to the last example. Here's a second order differential equation using the same notation we had previously. And notice here that we're saying the second derivative is equal to 2 times the first derivative minus 1. And so you'll notice here that I don't even have an x variable involved, but as long as I think about the relationship that it's stating, it will make perfect sense here. And this, of course, as I stated, a second order differential equation. All right, so let's go ahead and take a look at a simple differential equation problem. All right, so let's find all the functions that satisfy this differential equation here. dy dx is equal to secant squared x plus 2x plus 5. Go ahead and try that on your own. If you haven't noticed already, it would be very helpful to know your antiderivatives, and if you don't, to at least have a list handy so that you can start to learn them as we work through these. Try this on your own, and then we'll take a look at how your work should look and what the answer should be. All right, so we could do this in our head here, but I want to make pretty clear what it is that we're doing, what is the action that is taking place here. Well, here we're given an equation for the derivative of y with respect to x, which means that the function y is going to be the antiderivative with respect to x. And so what I can do is I can say, okay, what is that function? Well, that function y is going to be the antiderivative, or the indefinite integral, of this function here, secant squared x plus 2x plus 5 with respect to x. And I can find the antiderivative to this pretty easily in my head. The only sort of challenging one might be secant squared, and you will remember that the derivative of tangent x is secant squared x. So that's going to be tangent x. The antiderivative of 2x is x squared. And the antiderivative of 5 will be 5x. But I can't forget, of course, that there is a constant term that could be there that I need to make sure I include. So I need to have plus c here, where c is any constant. So this function y is the family of all functions that satisfy this differential equation. And notice how I use the term family. That is in reference to the fact that I could have any of infinitely many choices for my constant c. When I differentiate this back, taking the derivative with respect to x of both sides, I will get this differential equation. And you can see that clearly here. Now, there is a specific name that is given to this type of a solution to a differential equation. So if I'm given a differential equation, oftentimes I'm trying to find the function from which this derivative came. And when I do so in a general sense, meaning that I find the family, or in other words, all the possibilities here with my constant c, this is what's called a general solution. So let's go ahead and actually get this definition down. There are two different types of solutions that we're going to look at. Very similar, obviously, but important to know the difference. Okay, so our goal is going to be to solve differential equations. In other words, to find a function that satisfies the differential equation. In other words, to find the function whose derivative is given to us in the problem. And the way that we're going to do this, of course, is with anti-differentiation. And the symbol that we use for anti-differentiation is, of course, the integration symbol without limits, right? So this is called an indefinite integral. We haven't specified the limits here. And that represents taking the antiderivative of something with respect to whatever variable is designated. And we just did that in the previous question, and what we came up with is what's called a general solution. So that solution we got represented the family of functions because it had a constant c. It represented all the possibilities that we could have, right? C could have been anything from 5 to -1,000,000, and that equation would still have satisfied. So it is called a general solution. And the process by which I arrived at my general solution was illustrated in the problem we just did. Now, I want you to think back to when we were trying to figure out a particle's position, and all we were given was its velocity function. In other words, we were given the derivative of position. In order to find its position specifically, we needed not just the velocity, right? Not just its derivative of position. We also needed to know an initial condition, right? We needed to know where was that point that it started at. And that allowed us to ensure that we found an exact equation. And we can do the same thing here. So we can have what's called an initial condition. So if we are given both the differential equation and an initial condition, right, maybe telling me that the position was 4 at t equals 0, for example, we can solve for the value of c, thereby giving us one function that satisfies the situation, and this is called a particular solution. So the particular solution, being a single function, does not have a constant c there that could be any value, right? That's why it's called a general solution, and why a particular solution is called a particular solution. Now, problems of this nature, where I am given an initial condition, are what are called initial value problems. And initial value problems are going to show up on the AP test and are very useful in dealing with and modeling real-life situations. So we are going to solve many of them over the course of the next couple weeks and certainly on your AP test. So let's go ahead and get started by solving one now. All right, so here we have an initial value problem. Go ahead and copy this down and go through it once on your own. I guarantee that you can figure it out without too much effort. All right, hopefully you made good progress. Let's take a look at it together here. Consider the differential equation dy dx is equal to e to the x minus 6x squared. So a first order differential equation. Let y equals f of x be the particular solution to the differential equation with the initial condition f of 1 is equal to 0. So they're telling me a point that is on my curve y equals f of x, and they're telling me the derivative of y with respect to x. So what I'm going to try and do is put those two things together in order eventually in part B to find this particular solution. First, in part A, I'm asked what is the derivative, or f prime, at 1? Well, I know the derivative, dy dx, and so I can evaluate it at x equals 1, which is quite simple. I'll go ahead and show that work here. Notice, of course, that f prime of 1 is simply my derivative, dy dx, evaluated at x equals 1. And doing so, e to the 1 minus 6 times 1 squared is e minus 6, which is going to be somewhere around negative 3. And that, of course, means that the slope of my function, my particular solution, y equals f of x, is actually negative 3-ish at that point x equals 1. Okay, and to make this really clear what I mean by that, consider here this x and y axis. So here's the point 1, 0, and what I'm saying is that at this point, which I know the function intersects, the slope is around negative 3. And so if I were to draw a linear approximation, so a straight line that had a slope of negative 3 right at that point, it might look something like this. And that's what my function is doing right at that particular point. All right, now we're going to try and find the particular solution, actually write the function y equals f of x. So think about what we already know how to do. We already know how to find the general solution. In other words, the family of functions whose derivative will be this particular derivative that we are given. Well, that means that we know how all of those functions will look. The only thing that we have to determine is the value of c, right? That's what allows there to be infinitely many. So let's go ahead and find the general solution and then see if we can't use our initial condition, that extra piece of information, to determine what c will have to be in this case. So first step in doing that, I'm going to find the antiderivative of e to the x minus 6x squared with respect to x. And this shouldn't be too hard. The antiderivative of e to the x is e to the x. The antiderivative of negative 6x squared, well, the antiderivative of x squared is x cubed over 3, and 6 over 3 is 2, so it will be negative 2x cubed. And I can see, of course, that taking the derivative of this will give me 6x squared. And I have to include my constant of integration plus c. Now that I have my general solution, I need to find the particular solution. And that means that I need to identify exactly what the value of c must be. The only other piece of information I'm given is this initial condition, but that turns out to be exactly what I need. The initial condition tells me that when x is 1, y is equal to 0, meaning that that coordinate point, or in other words, an x value of 1 and a y value of 0, will satisfy my equation. So when I substitute that point, that x value of 1 and that y value of 0 into my general equation, the only thing I will have left that is unknown is this value of c, meaning that I can solve for c and determine my particular solution. So I'm going to use my initial condition here. And doing so, of course, allows me to rewrite my equation with x being equal to 1 and y being equal to 0 to give me 0 equals e to the 1 minus 2 times 1 cubed plus c. And doing so, I can now solve for c, which gives me c is equal to 2 minus e. Now, if I put these two pieces of information together, I take my general solution that I already found, and the fact that c must be 2 minus e, I can combine them to write my particular solution, which must be e to the x minus 2x cubed plus 2 minus e, as I have written right here. And just to prove that this is the particular solution, you could go ahead and you could first take the derivative with respect to x of both sides, and that would give you dy dx is equal to e to the x minus 6x squared. And you could also test out that the initial condition is satisfied. You could input an x value of 1, a y value of 0, and see that your equation is satisfied. One last little nugget of information to just keep in mind is that by finding the slope at 1, we were sort of painting a picture for what our function would look like at that instant by drawing that little straight line, and we're going to talk about that quite a bit more in the next lesson. So before we close out, let's just make sure we have a clear understanding of how we can solve these initial value problems. So as we just did when we were solving an initial value problem, we first want to find the general solution by anti-differentiating. That gives me the family of functions and leaves me with the constant c that I need to figure out. I use the initial condition to solve for c, and then once I have c, I write my function y equals f of x. All right, go ahead and complete the Unit 10.01 homework on Math Excel.